Did you know the term data science didn't even exist until 2008? As shown in our session earlier, many data scientists are switching careers to get into the industry. But what if you not only need to switch careers, but you don't even have an engineering background? The job of a non-technical business analyst is changing. There's more and more data being used to make critical, quantitative decisions. It's becoming common for people to do a bit of computational, analytical work as a part of their job, whatever that happens to be. Human resources, recruiting, product management, or sales. Some of those people do become enthusiasts and transition to full-fledged data scientist roles. In this talk, we'll discuss what that transition entails and look at how to achieve that goal. Gary Kazantsev is the head of machine learning engineering at Bloomberg, leading projects at the intersection of computational linguistics, machine learning, and finances. Prior to joining Bloomberg in 2007, Gary had earned degrees in physics, mathematics, and computer science from Boston University. He's a member of the KDD Data Science and Journalism Workshop Program Committee and a co-organizer of the annual Machine Learning and Finance Conference at Columbia University. Gary, why don't you show us your ways?
Thank you, Addison. Right. Um, so first, a little bit of an introduction. So this is the first time I'm giving this talk. So yes, I do, or rather until last week, I have led the machine learning engineering group at Bloomberg, which I started in 2009, so almost exactly 10 years ago, which at the time when I transitioned to a new role in the CTO office at Bloomberg last week was about 45 people. It started with just me and an intern. At this point, it's a part of a larger data science and AI engineering organization at Bloomberg, which numbers over 200 people working on a variety of different problems in applications of machine learning to finance, from natural language processing to speech to computer vision, time series analysis, anomaly detection, question answering, you name it. That group is composed of a number of people with rather diverse set of backgrounds. We have computer scientists, we have physicists, mathematicians, NLP experts, computer vision people, finance people, and crucially, a few people who have transitioned from a business background, which is why I thought I might have something to say about this topic, having managed people through this transition. It's a non-trivial transition, but before we talk about that, let's first talk about what does that mean? Who do we call data scientists? It has been described as the sexiest or the most important job of the 21st century. A couple of years ago, at which point everybody predictably wanted to become a data scientist, and therefore a whole lot of people started calling themselves that. Business analysts sometimes call themselves data scientists. AI researchers and engineers call themselves data scientists. Statisticians, economists, sociologists, marketing people, HR, everyone is a data scientist. So this moniker covers an enormous range of skills and an enormous range of problems. When I think about this, I think about three principal dimensions, right? About how to place people, right, in the skill set spectrum. So there is a question of business domain expertise, how much of a domain expert you are. The reason it's important is because, for instance, it's going to be very challenging for somebody to do data science in the medical field, right, if they don't even know the vocabulary, right, and do not understand what clinical trials are. The second dimension is the amount of programming or software engineering skill, and that ranges from people who just write things in R to people who build production systems in C++. And the third one is a mathematical background, which is going to control for how much innovation are you able to achieve in, for example, machine learning, which is one of the principal parts of the toolbox of a data scientist today. Depending on where you are in the spectrum, where you fit into this box, and where you want to be, your path and career options are going to be quite different. So who do we want to be? If you are starting from a non-engineering background, right, My opinion is that you would want to be somewhat of a jack of all trades, right? You're going to want to be a part mathematician or statistician, part engineer or programmer, right? Part data visualization person, and certainly part domain expert. There is one important distinction that we want to make in addition, right? My group was an engineering group, and we would like, I think, to separate machine learning engineers or AI engineers from data scientists, right? And the distinction is very simple. Are you going to be able and expected to build production applications? It's a similar skill set, modulo essentially the amount of programming and software engineering background that you have. Now, let's take this from first principles, right? To be a data scientist, I think that you should be a scientist first. What does that mean? This implies a certain appreciation for the scientific method and, importantly, an empiricist attitude towards data. Scientific method, right, consists of certain steps, right, or principles, right, observation, hypothesis generation, testing, which may mean confirming or invalidating, importantly, your hypotheses, and then rinse, repeat, right, and these are principles, not steps. The steps are going to be different depending on the actual domain. For example, in the medical domain, there are steps to this process which are not present in finance and vice versa. What does it mean to test hypotheses? Right? This is an important question, and this comes down to statistics. You will need to know statistics. Certain fundamental things like statistical significance and what does a central limit theorem mean, right? What kinds of metrics can you compute, right, for various kinds of statistical processes? These are crucial to your ability to actually test hypotheses. For example, in physical systems, there are well-established principles, right, for how many measurements do you need to obtain a confidence interval for something that you want to calculate. Other things that are important are going to vary by domain. For instance, in finance, when you are building trading strategies, and that is also nowadays a data science problem, you are going to be doing a kind of repetitive hypothesis testing. You generate an idea and then you try it out on so-called unseen or out of sample and preferably out of time sample data, and you do this many, many times for different hypotheses that you generated, right? Which means that you're looking at your unseen data many, many, many times, which means that that data is no longer really holdout data or really unseen. So you have to control for multiple testing. This is maybe not applicable, for instance, in things like marketing, right? Or in things like drug development. What does empiricist attitude toward data mean? By the way, this attitude is why physicists make for very good data scientists. Of course, I'm biased having been a physicist myself, but I have plenty of evidence. Something like between 10 and 20% of my group were from physics background. Data comes from a process, sometimes a physical process, sometimes a social process, right? But we have to understand this process as much as possible. Characteristics of a generating process for the data that you're working with is indispensable, both as priors as constraints. Does the data come from a physical process? Does it come from a poll? Does it come from some sort of game theoretical process? For instance, in finance, the price of Apple shares is a product of consensus of many actors. Those actors may have partial information, they may be boundedly rational. So the actual object, the price of shares of Apple, encodes quite a lot of very complicated information. Furthermore, right, that process may not be stable. It changes over time. In polling, the way questions are phrased and sequenced makes a huge difference due to phenomena such as anchoring, where the order in which you observe certain things influences your decisions for future events, right? If you're interested in learning more about that, the best way to do so is to read a very valuable book, which is called Thinking Fast and Slow by Kahneman, which makes an exhaustive treatment of these sorts of things. Does the process change over time? Right? This is a crucial question in finance, right? Because these sort of game theoretical consensus processes are obviously adversarial in nature, right? People will react to the behavior of other actors and behavior of the market more generally to outside events, right? So none of the things that define how this process works are stable. If it is not stable, you would like to know what the dynamics look like. What are the sources of error? Right? And this is an important question, which unfortunately is neglected in a lot of data science literature. Right? There is this larger topic of propagation of uncertainty in calculations, which is treated, of course, exhaustively in physics, right? Not so in other disciplines. For instance, if you make physical measurements of some sort, those measurements are going to have some error due to both systematic and kind of random effects. And the way that these errors propagate in calculations, right, is well described by theory in statistics. Is the experimental design sound? And this is a very important and potentially quite a complicated question. The difference in experimental design will make or break your data science project, right? And make the question that you're trying to answer either easily answerable or impossible. Some of the most famous experiments in history are due to clever design leading to cancellation of errors. For example, in physics, the Cavendish experiment, which uses a torsion pendulum in an unusual way, is able to estimate the gravitational constant, which is, by the way, of the order of 10 to the negative 11th, to 6 significant digits or more, depending on how accurate you are. Considering that that experiment was executed in the 18th century, this is quite a remarkable result. And I cannot promise that clever experimental design in the 21st century is going to produce as remarkable effects, right? But controlling for the sources and the kind of noise, right, in the measurements and in the samples of the data that you're collecting is going to make a big difference. Are you choosing the correct target variable? That's another important part of experimental design, which is frequently underappreciated. So, pertinent example, something that we have worked on for almost 10 years at this point. If you, for instance, are trying to solve an NLP problem like sentiment analysis, and you want to answer the question, is this news story going to be positive or negative about, say, Google, Apple, or Microsoft? The target variable is the most important part of the problem, because if you get that wrong, no amount of mathematics will help you. It turns out that if you don't give people any additional instructions when you pose them this question, you will get relatively low agreement rates. And multiple judges reading a news story is how you're generating your training data for this particular problem. So it is in your best interest to design a target variable in such a way that you will generate high quality consensus. So we had gone 10 years ago through about 6 months of experiments to arrive at a very carefully thought out target variable, which is something like this, which is if I'm an investor with a long position in this particular instrument, and I read this story in absence of other information, would I take this as a positive, negative, or neutral event? So the reason it's phrased this way is to try and debias people essentially, and to at least attempt to isolate effects of context. There's, of course, a fairly long and substantial list of additional guidelines to help people, right? But the design of this particular problem made for consensus of human beings somewhere between 82 and 92%, right, for freeway annotations, compared to, depending on the type of content, by the way, compared to somewhere between 60 and 70, right, without additional instructions. Other questions that you have to consider when dealing with data, right, have to do with bias, right? Do you have to deal with missing samples? Are the samples or features missing at random, or are they missing adversarially? If you're interested in pursuing this particular question, there is a very important paper from way back in 1994, which is called Learning from Incomplete Data by Garamani and Jordan, which I strongly encourage every aspiring data scientist to read. Really, the question isn't if the data is biased, it's really rather how it's biased. And understanding the kind of bias, right, and whether it is something that you can control for, I think is a crucial aspect of a data scientist job. These can be quite difficult questions. For example, just recently, about a week or two ago, a friend of mine who works for an electrical equipment manufacturing company came to me with a question. So the company manufactures smart home components, essentially, things which are controllers for other electrical equipment. So they have tens of thousands of these devices distributed around the United States, a large variety of different end user devices are connected to them. All these devices control things like power consumption, right, voltage, and so on, right, which is delivered to these devices in the end, and they all collect telemetry. So you have somewhere on the order of several tens of thousands different data streams, right, which come to you, relatively speaking, at random, depending on how people's clocks are set. And they report things like power consumption and voltage, resistance, and other electrical metrics. So his question was, how does he go about detecting anomalies in this data, right? To characterize failing components, right, or something genuinely wrong, like a fire, right? And there is maybe 20 or 30 kinds of devices. Every device exists in the field in multiple versions, maybe 10 or 12 different versions. So it can be quite a challenging task, right, if you start looking at the details. But because these are physical devices, right, you have very strong priors for how to think about this problem, right? No matter what you connect to such a controller, right, it's not going to draw a gigawatt of power, right? We're not connecting Death Stars to these things, right? We're connecting, lights and toasters, or maybe an industrial lathe at the high end, right? So these measurements that it collects, things like power and resistance and voltage, right, they have well-known physical interpretations, and they have certain very well-known relationships. So you can draw a box, right, in these 3 dimensions around what you would expect, right, from first principles. And that simplifies the problem considerably, even though the actual shape of this space, if you start looking at the details, can be quite complicated. So this is a kind of thing that I think is very valuable for people to be able to do, right? That is to say, think about the generating process of the data. Where do the measurements come from, and how does the underlying system work? Right? It will give you a great deal of guidance in terms of what methods you may or may not be able to use for the problem. Now, you will have to work with data, of course, right? Which today means that you're going to have to write code. Depending on what kind of code and how much, right, will determine whether you are a machine learning engineer or AI researcher or a data scientist of the statistician variety. I think it's safe to say at this point that Python has essentially won as a primary tool in a data scientist toolbox, at least over the last couple of years. It used to be 10 or 12 years ago when I just started our machine learning group that people wrote in MATLAB and in R, people wrote in various niche languages, functional languages, in SAS, and so on and so forth. Over the last couple of years, vast majority of people have converted to Python for pretty much everything that we do in terms of prototyping. And I think that is generally the case around the industry. More and more people are standardizing around the Python kind of ecosystem and the very important and valuable tools that have been built in this ecosystem. Now, of course, there are other more specialized tools, right, which still have their place, right? So, for instance, in finance, there are various derivatives of APL, like K or Q, right, that are used by quants in the, particularly in strategy development and time series analysis types of applications, right? More generally, why would you write code if grep and cut and sort and word count will do the job in 10 seconds, right? So the general statement here is that you should know your tools. Right? The better you know your tools, the better you are at programming or using your environment, the more effective you will be as a data scientist. The know your tools part will also apply pretty much without change to the mathematical methods. Right? You should understand what assumptions does the model you are using is making. Nowadays, statistical methods increasingly imply machine learning, right? But this applies even to basic statistics like linear regression. Right? What assumptions do linear regression models make? Well, there is a couple, right? There is linearity or additivity of the effects. There is statistical independence of errors, which means no autocorrelation, homoscedasticity, which means basically constant variance of errors versus time versus predicted variables versus other independent variables, and normality of the error distribution. Relatively few people, it turns out, actually understand linear regression, really understand how it works, which is kind of disappointing. What does that mean for our understanding of, say, deep neural networks? The way that I think about these kinds of questions, right, which model might be appropriate for this particular kind of data, being a physicist and a mathematician, the most natural tool that I reach for is geometry. Now, it may not be a fit for everyone, but to me, has been a very useful part of the toolbox to think about what kind of relationships, right, between variables does the data encode, and therefore what kinds of methods would be apt to use, right, to represent these kinds of relationships. The more modern approach to this sort of thinking is actually called information geometry. This kind of thinking about the assumptions that your models are making is something that gets drilled into you in statistics, right, but is unfortunately frequently missing from modern machine learning today. What all of this means, the know your tools, understand the assumptions, is mainly that you cannot just throw algorithms at a problem until something sticks. You have to explain, if you are to be a data scientist, right, why something works. Right? If you build a predictive model right? You have to be able to explain why does it work and why should you expect it to continue to work in the face of a changing world. As we apply these methods, right, from machine learning or statistics, from data science, right, to increasingly important problems in medical diagnosis, in drug discovery, in things like self-driving cars, criminal justice, uh, hiring decisions, educational decisions, right? This becomes ever more important, right? Which is why interpretability of machine learning models is an increasingly important area of research. Right? If you want to pursue that kind of research, right, there is never enough mathematics that you can know, right? This is a somewhat different subject because this is getting into what does it take to be an artificial intelligence researcher, right? And there is a very different kind of skill set that you require for that, mainly having to do with mathematics. But hopefully this gives you an idea, right, of what a data scientist, the way that I think about data scientists should look like. So I have had 2 or 3 cases of people who have actually transitioned in this fashion, people with business and economics background who were actually able to join my team. Right? In one particularly representative case, that transition took about a year. Right? So this is a lot to learn, but having determination and perseverance, right, and following this kind of blueprint, what I just described, has been demonstrated to be successful, even in cases where you end up in engineering group where you have to build production applications.
Gary, thanks so much. We appreciate all of that. We did have a couple questions come in, and I want to see your thoughts on a few of them. Again, thank you so much for your time. I know this has been very helpful for a lot of individuals who have been watching online. For those of you who are still watching, again, if you have any questions you would like to ask, feel free to post them in either the YouTube live chat or in our Slack channel. And again, Gary has mentioned that he will be online for a little bit longer after this as well. First question came in from a Lucas L. Now, Lucas L asked, in your experience, what are the advantages that new data scientists who might come from a field outside of a hard science like physics, math, engineering, or chemistry, what are some of the advantages that they would have in comparison to somebody that does come from a science-based field? And Lucas himself is a physicist and says that he finds them to be better communicators. What would you say about those individuals?
Right. So in my experience, people who come from not from a hard science background, but from some sort of business or economics background tend to have a lot more domain knowledge, right? And that's a big advantage. I think it's going to be very difficult, like I said in the beginning, for somebody to be successful as a data scientist, say in medicine or biology, right? Because somebody coming in from a hard science background wouldn't even know the vocabulary, right? For describing the data, forget knowing something about the relationships, right? That data might represent. Communication is, I think, a kind of independent variable in this case, right? Because if you deal with people from the hard sciences background, there's a spectrum of communication skills, right? And similarly, there is going to be a spectrum of communication skills for people with business or economics background. Right? Some people are good at this. Some people are, not very good at this. It's always an advantage, right? And I think it is a crucial part, right, of what a data scientist is supposed to do, right? Because inevitably, in one way or another, you're going to have to communicate your results. I didn't talk at all about data viz kind of stuff, right? Because I myself am not an expert at it, right? But if you're able to build a compelling presentation, right, and to kind of accurately represent your results, right, I think that is universally an advantage, no matter what you're doing.
Right.
So people who come from the background where they had to do that, build pitches or presentations, right, do data visualization, right, they are going to be at the comparative advantage, right, to people who have only ever dealt with numbers.
So let me ask you sort of a follow-up question that switches the question. For those individuals who have come from data science from a hard science background and maybe looking for opportunities to expand some of their non-engineering knowledge, would you have any recommendations or advice for them?
That's an interesting one. So I can look backwards on my own experience, right? I came from a science background. I didn't know anything about finance, right, when I started at Bloomberg, right? And I had done everything, I guess, that you can think of. I had taken courses, right? I read on my own. I read papers, right? And I learned by osmosis, right, by talking to people. So if you're transitioning to a different kind of business field or different uh, uh, kind of taking a different direction, right, I think you will probably need to do all of those things. And I think it will vary depending on the domain of your choice, what the specific resources that you might want to use are going to be, right? So I can give suggestions for natural language processing, right,
Right.
or for finance, right. I am afraid I'm not going to be able to give very high quality suggestions for genetics.
Right. No, understood. Understood. So one question came in from someone named Richard, and 2 days ago we had a presentation by the head of Kaggle Learn, Dan Becker. He was highlighting what makes a data scientist, and Richard commented that your position seems to be very different than Dan's. Specifically, it relates to this question: who is a real data scientist? So would you say more so data scientists by 6 months of a boot camp training, or data scientists with rigorous training who can make a contribution to the field? So would you want to elaborate a little bit more on that?
Oh, that's what I think the substance of my talk was about, right? So like the things that I described is what would make for a real data scientist to me, right? So again, some appreciation for the scientific method, empiricist attitude toward data, right? Knowing your tools, right? Having mathematical background that allows you to basically separate noise from signal in a rigorous way, right? It doesn't matter how you arrive by that skill set, whether it's a 6-week bootcamp program or 6 years of formal education
Right.
in hard sciences, right? Like if you're able to achieve that in a 6-week bootcamp, I envy you, right? But the end
Maybe not
result is
realistic. Right.
but the end result is what matters. So somebody who has never done anything uh, kind of in this kind of statistics sense, right? Who doesn't know what a Gaussian looks like, uh, it's going to be a challenge, right? Because they may they may be an analyst, right? But I don't think you would be able to call yourself a data scientist.
Right. That's valid. It's a valid perspective. This question came in from our YouTube chat. It was from a Sequoia Wycliffe. Why do you think Python is the leading tool for data scientists nowadays?
Just based on experience. This is what I have seen kind of across last 10 years worth of work in this field, and having talked to hundreds of people both in the financial industry and in other parts of in other industries.
I'm sure the users of R are currently vehemently disagreeing with you in our conversation right now. But
like I said, it's not that there aren't other tools, and yes, other tools have their place, right? Python, as compared to R, right, is a general purpose programming language. You can build anything you want in it, right? And by virtue of that fact, right, it will expose you to a much broader range of abstractions, right, and therefore give you a much broader perspective in terms of what you can do with computation, right? I think that is fairly uncontroversial. Now, of course, if you have years of experience in R and are able to do your work productively, great. Kind of, I have no question that that is valid for many, many people, right? But I think even for those people, my suggestion would be to learn a general purpose programming language, and that language that I would choose for a newcomer to kind of to this field to learn would be Python.
Right.
Right?
Very valid.
Now,
Yeah, I think
if you have both of these things, you will be a better rounded person.
right. Admittedly, I sometimes just like to spark debate for the sake of debate when it comes to Python and R, but I think it's a great answer. Francis had a question, more so clarifying a comment you made a little bit earlier. What did you mean when you say that most people don't understand linear regression? Or specifically, what disappoints you about the responses? They had a little bit of trouble hearing the rest, so if you wouldn't mind sort of reemphasizing and clarifying that comment.
Right, so linear regression makes certain about the data, right? And in particular, about the errors, right, that you are observing in the data, right? So what disappoints me frequently, right, when I talk to people, right, and this is not specific to linear regression, but pertinent example, right? People compute something like Pearson correlation of two variables or something like that, and they observe that the correlation is 0, right? And they completely ignore the possibility that the relationship might be just nonlinear, right? And that this test doesn't mean anything, right? Unless you actually test for that specifically, right? Like if your data exhibits, multiple collinearity or something like that, right? Or autocorrelation in terms of time series kind of sense, right? Like your linear regression results are meaningless. At best, it's going to be inefficient at predicting what you want to actually know. At worst, it's going to be badly misleading, right? And it's not like this is a secret. Linear regression has been studied, right, for decades and decades, right? And there are well-known tests for all of these things, right? Kolmogorov-Smirnov test and what have you, right? So if you read an actual statistics book about linear regression, you will understand what I mean, right? Kind of unfortunately, a large number of people, to them, basically, it's just a black box, right? Which is a peculiar phrase to apply to linear regression. But,
Right.
But people don't necessarily understand what are they using.
Right. So Timothy Salazar had a question that was somewhat similar, and maybe you could use a different example. He asked, do you have an example of when error analysis, or maybe even the lack of error analysis, made a big impact on a data science problem?
Yeah, easy example. So again, I will come back to the problem that I have spent a lot of time on, right, which is sentiment analysis. So this is a natural language processing problem. Nowadays, it's getting more and more commoditized, but 10 years ago, this was kind of exotic. So suppose you collect documents from, say, 2 years, right, worth of history, right, and you sample documents across different sizes of companies and across different industries. You ensure kind of some sort of reasonable coverage, right, in terms of time, right, and then you have humans annotate that data, and you hold out, the last 6 months of that data for testing. You build your model using, let's assume for the sake of argument, using something fairly simple to start. So not, stacked LSTMs, but rather something like logistic regression, right? Or random forest sort of thing. So you learn your model, right? And it exhibits a, say F-score, macro F-score across the different classes of whatever, 0.7, 0.75, something like that, right? So you did everything correctly, in a sense, right? So like your data is actually out of sample, it is temporary in order so that you are guaranteed not to borrow information from the future, right? And you observe that it performs well, should you go with this model to production? And the answer is, unless you actually look at the data and you understand what kinds of errors is it making, the answer is no, you shouldn't. Because first of all, the errors here are not necessarily equally costly, right? Because confusing something which is positive with something which is neutral is a lot less damaging than confusing something which is negative with something which is positive.
Right.
Right. So that's number one. Number two, let's assume for the sake of argument that you didn't do much feature engineering, right? It's whatever, n-grams, right? With some reasonable stop words list, or with a stop words list that looked reasonable. And it just so happened that in Q4 of both of the years from which you sampled your data, right, because of cyclical economic effects, it just so happened that predominantly the news were negative. Unless you inject prior knowledge into this problem, right, or unless you look at the actual features, right, your model will happily learn that date expressions relating to Q4 are negative, which is nonsense because this is a time invariant phenomenon.
Right.
Right. So yes, right, it will happily learn names of entities and people, right, which is not invalid, right, but it's not useful for purposes of building predictive models, right? So this is an example, right, that we have spent a lot of time on, right, which is why it's easiest to want to reach for, but the phenomenon is very, very general.
Yeah.
So
and
this is
actually,
something that
as I mentioned, just a question that someone else asked that seems to, it's kind of taking what you're just mentioning, but making it a little bit broader. Daniel Rankin asked, can you speak more about explainability? Why is it so valuable to a data scientist to be able to explain why something works?
Right. Well, the example that I just gave maybe gives people a little bit of an idea.
Yeah, exactly.
This is even more important in genuinely mission critical applications, right? Like if you are building something which is a computer vision system which is supposed to do cancer screening or something like that on the basis of photographs of people's skin, right? And the model is going to basically decide your course of treatment, right? Like you would really like to know why it thought you had cancer.
Right.
Right. At least I would like to know. Because even if I am talking to experts which are humans, in that case, I would go and get a second opinion, right?
Yeah.
And people understand this, right? At least they understand this more and more, right? We encountered this problem head on 10 years ago because we built, as a result of the experiments that I mentioned on sentiment analysis, fairly complex stuff. So we built nonlinear ensembles of nonlinear support vector machines, right? RBF kernels, thousands of features, thousands of support vectors and whatnot. And those models are, relatively speaking, quite opaque. Right? There is not a lot of ways to back off from that one to something which is explainable to human beings. Like you can't even extract weights for features from it, not very easily anyway. And even though those models were competitive with human judgment, they were very good, at least by, certainly by 10 years ago standards and even by today's standards. People wouldn't buy the results because it was not possible to explain them. Right? Not in a way that, logistic regression is quote unquote explainable in the sense that you can actually look at weights for features.
Right.
And the features will make sense to people because they're words.
Yeah, that's no. I mean, yeah, I think that's probably one of the most clearest examples is so it's cancer. If someone says I have cancer, you better go explain why and how and make sure that things are going in the right direction.
Well, there is also a regulatory aspect to this, right? So, GDPR most recently, state of California, I think, is supposed to put into practice law, which is essentially GDPR kind of prime, right? Next year. In finance, this is actually a regulatory environment that we have been in for years, right? If you're doing advising in terms of investment advising, right, you have to be able to explain, right, in kind of some sort of human understandable terms, why did the model make a certain decision, especially, for instance, if you're denying somebody credit.
Right. Yeah, no, completely agree and understand that when it starts getting, there's a whole other conversation around ethics and machine learning, and that can be brought up there as well. Final question for you. This came from a Timothy Yee. What resources could you recommend for non-engineers and those with little to no background in math, statistics, and science to develop some pretty serious skills pretty fast?
Right. Fast is going to be a relative term.
Sure.
So the mathematics part and machine learning part is one direction, and then the computational stuff is another direction. So for the computational stuff, right, I have my own preferences in terms of what I would recommend. There are some classical books, right, and there are lectures which are based on those books, which I think are very, very valuable, right, and which I personally have missed in the sense of when I was going through my education, these resources were not available.
Right.
So I envy people who are starting in this field in a way today, right? So there is structure and interpretation of computer programs, right? And there are lectures based on that. Right? There are classical books by Kernighan, right? So practice of programming, the C programming language, which will teach you much, much more than C programming language, by the way. And there are maybe a few others, but I think if you start with those 2 or 3, right, you will be a much better programmer, right, than many people kind of who come out of computer science programs.
Right.
If you really understand what these books actually talk about, particularly the SICB thing.
I'll say Jason Siegel had a follow-up question with that. You mentioned earlier an individual with an economics background who successfully transitioned to your team. And
yes.
They're curious if you were aware of the tools that he or she used to achieve that level of expertise in that first year.
Yes, of course, because I suggested those tools to them. All right, which are the tools that I'm suggesting right now.
Right.
Okay. So this is on the computational side, right? And then the rest of the kind of, besides book learning, right, there is just practice, right? And this is a much more broad and kind of personal thing, right? So some people like, Project Euler kind of exercises, right? Some people, right, have other interests, right? But the end result is basically you have to write a certain number of lines of code, right, to be able to be comfortable with the tools that you're using.
Right.
And the critical threshold, at least in my experience, seems to be something like, you have to write at least one, preferably more, program which is at least 1,000 lines long in the language of interest, right? So like past that point, like until you hit that threshold, you will simply not have encountered certain things. Right, certain issues which are quite important. So on the mathematics side, the thing that underlies a lot of the current machine learning and more and more actually of the current machine learning stuff is actually linear algebra, right? So, and there are a large number of different books on linear algebra, right? My personal favorite as a mathematician, of course, is Finite Dimensional Vector Spaces by Haumash. It's a classical book. But for people who are more kind of interested in applications, there is Gilbert Strang book or books, right? The most recent one being, I think, Linear Algebra with Applications. And there are lectures based on both of these things for free online, right? Taught by Strang himself, actually.
That's great.
besides linear algebra, kind of for statistics, again, there is a zoo of different resources. There is Wasserman's book, which is all of statistics, right? There is kind of a more a less mathematical treatment of the common errors that people make. Is a very interesting and useful book, which is called Statistics Done Wrong. That's a good one. But that's a very deep field, right? Like that, you spend a lifetime learning.
Right.
You know, another kind of, so, and again, statistics and probability theory in this case are quite close together, right? And for probability theory, I would have to think more carefully about what to recommend, because my personal experience is, again, coming from hard sciences background, right? The kinds of things that I'm going to be able to recommend off the top of my head are probably not the most useful,
Right.
To somebody who is just starting, because they're going to kind of, the kinds of references that I'm thinking about, they will require analysis, right? And people who are coming from non-hard sciences background are not going to have analysis. Right, and for machine learning, I think there are two books, right, that I would recommend wholeheartedly. One is called The Machine Learning: A Probabilistic Perspective by Murphy. It's from 2013, right? But it's quite good. Very clear, mathematically well-grounded, lucid, right? It doesn't have a lot of stuff on neural networks, right? But for that, there is the Goodfellow and Company book, which is deep learning, right? So if you read those two, right, you will be able to read any paper currently being written.
Right.
That's the summary of my suggestions.
That's fantastic, and I'm sure there are people all throughout the chat who are just frantically trying to type out and rewind and see what those books are. Gary, thank you so much for your time. To all those who are watching, Gary has graciously agreed to continue to answer a few more questions in the CareerCon Slack channel. So please be sure to ask any additional questions in that channel as you may have them. Maybe he'll also retype some of those books for you, as I know a lot of those were coming in all at once. Very valuable, very practical advice. Gary, again, thank you so much. Next up, we're going to be going offline here a little bit on the video to go digital for our career fair. So go to the Slack channel, which is #CareerFair, to find more instructions from our Slack community manager, Paul. Meet dozens of companies and educational institutions like Airbnb and Coursera with opportunities to connect, share interests, and learn more about next steps in getting connected with each of those. So we'll see you on Slack, and we'll be back here at 3 o'clock Pacific time. We'll answer the question, what exactly are hiring managers looking for? So we'll see you then.